In this video, you're going to learn how to perform a spectral derivative in 2 dimensions using the NumPy.FFT routines. For this, we will take a very simple function and then look at its 2 analytical derivatives, first in the x0 direction and then in the x1 direction. Then we will discuss how to create a Wavenumber grid that is relevant to define the derivative or gradient operator. And ultimately, we can then use this operator to take the spectral derivatives, and we will see that they very closely match the analytical derivatives up to machine precision. Let's get started. The channel sponsor, Pasteur Labs, is currently hiring SciML and software engineering positions. Check out pasteurlabs.ai/careers for more details. Hi and welcome to this new video where we will extend the idea of taking spectral derivatives to 2 dimensions. If you watched the 1D video that I've linked up here, you probably noticed that there's quite some details of moving from the continuous description that you might learn in a textbook of how to take spectral derivatives to how to actually perform it on the computer. Here we will take the idea into 2 dimensions. So now our function depends on a vector, or this vector is basically the 2 coordinates, so an x0 and an x1. For simplicity, we only have a function that outputs a scalar value, so you can, for instance, think of it as a surface landscape over a 2-dimensional map. Now we are interested in a derivative, and since we are in 2 dimensions, the derivative is a bit arbitrary. So more precisely, we are interested in the gradient, so which is the collection of the partial derivative with respect to the 0th entry and the 1st entry. And we can get that in a very similar fashion, at least conceptually, by performing a Fourier transform, multiplying with the wave numbers, and then inverse transforming. Since we are in 2D, we need to move to the 2-dimensional FFT, which is also handily available in NumPy. But now the bigger difference is that our wave numbers, at least discretely speaking, is now no longer a vector, a 1-dimensional vector with the number of wave numbers that we have, but rather it will be a 3-axis tensor. So we will have for each grid point, we have a 2-dimensional vector wave number, and we will see that later. And that also kind of makes sense because if we do the gradient operator, we actually get a function that no longer returns a scalar, but returns a gradient. So for each point in the domain, it associates a gradient or a vector. And so we also have that somewhat within this derivative formula. But I'm pretty sure this will come clear once we implement that. So let's get started. Let's first import NumPy as NP. And then we also need matplotlib.pyplot as PLT. And then let's define the problem domain that we're on. So for now, I want to have a domain which is of the same extent in both dimensions and also uses the same number of degrees of freedom. So let's say L is 1. So we have a unit square domain and N shall be 100. And let me just add the remark. We assuming the domain is from 0 to L squared. So it is the 2-dimensional domain with identical number of grid points in each direction. And I want to say for now, because of course the idea generalizes to more complicated domains, but this is left out for a future video. Okay, next up, I want to create the mesh. So for this, let's first start with the 1-dimensional mesh, which is the same in both dimensions. So let's just call it mesh 1D. And this one is numpy.linspace from 0 to L with 100 points. But if you watch the video on the 1D FFT, you notice that by convention, we have to remove one of the boundary points. So either the left or the right boundary point. Typically one does the right point. So we will set endpoint equals false. And if we then take a look at this mesh 1D, you notice that it starts at 0, but it does not include the point 1.0. And that is very important. So therefore I also want to leave the remark here. So this is very important. The endpoint is not included, and this is an FFT convention, or the FFT call we will use later on implicitly assumes that. As said, this is now just a 1-dimensional mesh, so it's just a vector or a 1-axis array. Now we want to get our 2-dimensional mesh. For this we will use the mesh grid function and compute an x and y with np.meshGrid on mesh 1D and mesh 1D. And x and y are basically now n by n dimensional matrices or 2-axis arrays. So we can take a look at that. So 100 by 100. And if you look into the entries, you notice that they are repeated and then stacked together. The X array is repeated in this direction and the Y array is repeated in this direction. But we want to keep that together, so we will create a 3-axis tensor, and let's call this the mesh. And for this we will stack X and Y together, so NumPy.stack on X and Y. And if we take a look at the mesh, we will now see that it is a 2 by 100 by 100 tensor or array, so it has 3 axes. And if we index it at in its 0th axis, in index 0, we essentially get back X, and if we index it at 1, we will get back the Y. So this is just a handy way of combining this together. Okay, now that we have the mesh, let's define the function we actually want to differentiate. And here it just shows a very simple function. So let's say f is a lambda function which takes x, and now x is assumed to be a vector, and a 2-dimensional vector with a coordinate in our 2-dimensional space. And then it returns NumPy.sign on 2 times NumPy.py multiplied with x0. So basically it's the first sign mode on the x0 direction, and then we multiply it with NumPy.sign on 4 times NumPy.py times x1. So basically this is the second mode in y direction. For this function we can analytically derive the derivative. So we have a derivative in x0 direction and in x1 direction. So let's first do the x0 direction. So we do lambda on x, and if we derive that function with respect to x0, we can ignore the second part, so only have to consider the first part. And then we do the outer derivative, which is NumPy cosine of this whatever is inside, and the inner derivative is just 2 times NumPy.py. So we get 2 times NumPy.py times NumPy.cosine on 2 times NumPy.py times x0, and then the second part just stays as is. So times NumPy.sign on 4 times NumPy.py times x1. Same procedure for the derivative in x1 direction. So fx1 is again taking our coordinate vector, and this time the first part stays as is. So we will get NumPy.sign on 2 times NumPy.py times x0. And now the derivative here is, so let's first do the inner one, which just gives us 4 times NumPy. So 4 times NumPy.py times NumPy.cosine on 4 times NumPy.py times x1. So basically now we have the 2 entries in the gradient separate. So we could have also defined a function gradient, which instead of returning a scalar, returned a vector. But here I wanted to keep them separate. Okay, and then let's discretize the 3 functions on our mesh. So let's say fh, in order to indicate that this is the discretized version, is f applied to the mesh. Then we have fx0h, so the partial derivative with respect to x0 discretized on the mesh. Just because we're taking a derivative does not change the nature of its dependency, so it will still be dependent on the mesh. And as such, we also get like this 2-dimensional matrix out of it, or 2-axis matrix that we can then plot. So let's do fx0 applied to mesh, and fx1h is fx1 applied to mesh. Then let's shift enter, and we can also check the shapes. So fh.shape, fx0h.shape, and fx1h.shape. And we get all of them are 100 by 100 dimensional arrays. Okay, let's delete that line again, and then let us plot all of them together. For this I will first paste in a handy plotting function. Let's quickly go over what it does. It takes a variable number of positional arguments that depict fields, and then also some additional keyword arguments, and essentially it creates a grid figure from matplotlib and plots all of the fields as filled contour functions within there. and make some additional modifications, and also adds a color bar to the very right for all of the plots because all of them share the same color mapping. So let's shift enter that function and then use it to plot the original function as well as two partial derivatives next to each other. So let's do plot to contour row on fh, fx0h, and fx1h. Okay, maybe we use the semicolon to suppress the output, but here we go. Now we have our plot all together. The very left is our original function, and we see we have an x0 direction and we have an x1 direction, and then basically with the contours we see the value of the function. A blue value indicates a negative value and the red a positive value, and the color map is centered around 0. And this also represents the functional form we had. So we have as originally a function that is a first sine mode in x direction. And if you, for instance, take out a line here and look at it, so first it goes up like a sine, and then it goes down into the blue valley, and then in the x1 or y direction we have the second sine mode, so we do 2 periods, and it is also noticeable, so we go first up, then we go down, then we go up, and then we go down, and then we are at 0 again. Then to the right we have the two partial derivatives. So we have the partial derivative in x0 direction. So this is as if we take out the line, which was a sine, and then derive it, which gave us a cosine, and the cosine starts at +1. So we start at +1, which is red, and you cannot see it here because it clips. Because next to us getting a functional form of a cosine in x0 direction, we also get the scaling of 2 times pi. Pi is around 3.1 and 2 times pi will give us around 6.2. So the value that is whatever inside of this shape here actually clips because it is way above 1.0 that is used as the upper limit for the color scale. But still we see that we start at a positive value, then we have cross 0, we go into a negative range, then we cross 0 again, and then we are at a positive. And this is essentially a cosine. But importantly now, we keep the sign in x1 direction, because we noticed when we took the partial derivative, the second part that was multiplied stayed the same. Now for the partial derivative with respect to x1, we see the pattern in the opposite direction. So now we get in x1 a cosine, so starting at a positive value and so on and so forth. I think you get the point. And then in x0 direction, we keep the sign. And one more point I want to highlight here is that if you look very sharply to, for instance, this plot here, you see that the value of the reds that is still plotted here, there is still a little gap between the left point or left part of the plotting boundary. Maybe I can open that into a separate plot and zoom a little bit in. So I mean that part here versus this part. And the reason we see this one being closer to the rim of the plotting part is because we did not include the right point in the mesh. And this is also the reason you don't see a 1.0 in the ticks. So there is no ticking of 1.0 here in this direction and this direction for all of the plots. And as said, this is relevant because it is an FFT convention, and also efficiently speaking, it can be necessary because that is a redundant point. If we are in a periodic domain, we only need to prescribe or know one of the boundaries because the other one can be inferred. Okay, long story short, this was a lot of preparation. Let's get into the part of taking the spectral derivative. So for this, we do a very similar approach to how we created the mesh. Okay, for this we will start with first creating the wave numbers in 1D, and that is very close to what we had in the video. So we used the handy function NumPy.FFT frequencies on n, so to get the corresponding wave numbers for n degrees of freedom, and then the spacing shall be 1 divided by n, so that we basically get the correct values here. But then crucially, what you also saw in the 1D video, that is not sufficient to create the true wave numbers, because in spatial Fourier transforms, the wave numbers depend on the domain length. And this kind of also makes sense because the eigenmodes, or these eigenfunctions that we handily chose here as consisting of sine and cosines, they change depending on how long the domain is. And this needs to be reflected in these wave numbers. So we need to multiply them with a scaling, which is 2 times NumPy.Pi divided by L. So L is just 1, so this will just give us 2 times NumPy being scaled with that. So we can also take a quick look at it. So basically, this is a special way of ordering them. So we have a 0 in the beginning, and then we have ascending all the positive wave numbers. And you now see there is no longer an 1, 2, 3, 4, 5 that you might expect with an ordering, but rather they are scaled with 2 pi. I mean, you see 2 pi is approximately 6.28 apparently. And so we have 0, then 1 times 2 pi, 2 times 2 pi, 3 times 2 pi, 4 times 2 pi, la 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 la, and so on and so forth, all the way to 307.87. And then afterwards, we have the negative wave numbers also in ascending order. So we start at minus 314, then 307.87, minus all the way down to minus 6.28. Okay. But we're not too concerned with the values right now, because we kind of know that this is the right way to create the wave numbers. So let's close that. But now we have to also move them into 2 dimensions. So we need to do something similar to them with the mesh. So we will do a mesh grid. And so we get a kx and a ky. So these are essentially the wave numbers in x and the wave numbers in y direction. Or you could also x0 and x1 direction with np.meshGrid on wave numbers 1D, comma wave numbers 1D. And again, the idea is similar. So kx now is a tensor of 100 by 100. And if you take a look at its values, you see that it has the same ordering, or the same vector essentially repeated over the row dimension. And for the ky, it is repeated over the column dimension. And now we want to do something similar to with the mesh, in that we stack them together. So we get the wave numbers by doing numpy.stack on kx, ky, and then we can take a look at its shape, and we see that its shape is 2 by 100 by 100. So it's the same as with the mesh. With the wave numbers, we can then define the derivative operator. And the derivative operator is purely 1j, so the imaginary unit in Python multiplied with the wave numbers. So this does not change the shape, so it's just each entry is multiplied with the imaginary unit. It is better to call it the gradient operator, because now it actually, if we were to multiply it with a transformed field, it would take the derivatives both with respect to x0 and x1. So let me note that down. So more precisely, it would rather be called the gradient operator, and that is because as it accumulates all partial derivatives. Okay, then we can use it to take the spectral derivative. So let's do f x0 h spectrally is essentially the NumPy.FFT IFFT2, and 2 stands for the 2-dimensional FFT. There is also the general case of the n-dimensional FFT. So the idea we have so far with mesh gridding and getting the wave number operators extends also to 3D, and if you want higher dimension as well. So let's take a look at it. So this basically then requires you to hand over the axes over which you want to perform the Fourier transform. And for all the other axes that you do not mention, you perform a batched operation. But for us, we just stick to 2D and do NP.FFT IFFT2. And then we need to also forward transform. So we do FFT2 applied to FH. And then in order to get the derivative, we will multiply the derivative operator. But now the derivative operator was the gradient operator. In order to take the derivative with respect to x0, we index at 0. And then, if you recall, the IFFT2, or more generally Fourier transforms, they work within some numerical rounding errors. So despite, of course, us knowing that the derivative is real valued function, so because if we take the derivative of a real function, then we still have a real function, but it would still return an imaginary component, albeit it being very small. So it is around 10 to the minus 15, 10 to the minus 16. But we can just drop it by saying dot real. So this is the spectral derivatives. Let's plot it next to the analytical derivative. So let's do fx0h and fx0h spectrally, and again suppress the output. And here you go. So the left is the analytical one and the right one is the spectrally obtained one, and they are very close. So let's also compute a difference and relative error numerically. So let's say NumPy.linalg and then .norm to get the 2 norm of fx0h spectrally minus fx0h, and then we divide that by NumPy.linalg.norm of fx0h. And that is a very small value. So this is almost the machine precision, so unnoticeable. So we did a very good spectral derivative here. And I mean, to some extent that works because the function we use is band limited. That means we can exactly represent it in the grid that we have. So, or the Fourier transform exactly represents it, because I mean, we only used the first 2 modes. So the first mode in x direction and the second mode in y direction. And we had 100 degrees of freedom. So that's totally below the Nyquist criterion. But still, I think it's interesting to see that we can use the FFT to obtain this derivative. Okay, next up, let's also do the derivative in x1 direction. So let's say fx1 spectrally. Sorry, this is fx0 spectrally. fx1 spectrally is the same idea. NumPy.FFT IFFT2 applied to, let's scroll down, the derivative operator indexed at 1 multiplied with NumPy.FFT.FFT2 of fh, and then again dot real. Then we can also plot it. So plot contour row on fx1h and fx1h spectrally and suppress the output. And here we notice they also qualitatively look very similar. And then let's compute a numeric value in their comparison. So NumPy.linalg.norm of fx1 spectrally minus fx1h divided by NumPy.linalg.norm of fx1h. And that's also a small value similar to the one we had here. Okay, last thing I want to show you is how to take the gradient. So because now we used each of the direction of derivatives separately, but we can also get the gradient by saying grad fh spectrally. And this essentially is NumPy.FFT.IFFT2 applied to the derivative operator multiplied with NumPy.FFT.FFT2 applied to fh and then dot real. This works, and I will quickly discuss it. Let's just look at the shape. So grad fh spectrally dot shape now has 2 by 100 by 100. So each of its entries is essentially the spectral component we just computed. So how does that work? So if we apply the FFT2 to FH, we can also take a look at it. NumPy.FFT, FFT2 applied to FH, and then look at the shape. We see it's still 100 by 100. But if we now take the derivative operator, that is 2 by 100 by 100, and element-wise multiply it with that array, we will do an auto-broadcasting. So basically, the result of this operation will be an array that is 2 by 100 by 100. And if we then use the inverse Fourier transformation 2, it will compute the FFT or the inverse FFT over the last 2 axes, but it batches over that axis. And as such, we then also return that shape. And just a quick note that if your function is already vector valued or vector output, so that it does not only map to a one-dimensional quantity, you need to make sure that this broadcasting works right. Oftentimes what you could, for instance, do is to add a singleton dimension to then get, instead of two 100 by 100, your output dimension, derivative dimension, and then the spatial dimension. But this is of course a bit more of an advanced topic. This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also, a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. And if you also want to see that in action, I have a couple of videos that employ spectral derivatives to perform simulations. And you also see spectral derivatives to some extent also in deep learning. A lot of the methods that are now applied in neural operators, for instance TFNOs, kind of relate to how we do spectral derivatives and pseudospectral methods. So there's a lot of similarities between that. So stay tuned for a lot of videos that explore these similarities. Here you will now see similar videos, and I hope to see you in one of the next videos.